Children, I hope you have gone through my previous videos and done all the work that was assigned to you. Let us now proceed further. Today we are going to study about chemical kinetics. Chemical kinetics is the study of rate of chemical reaction and the mechanism by which they proceed. Now, on the basis of rate of chemical reactions, they are of three types. First is instantaneous or very fast reactions. In this category come all the ionic reactions. Second is very slow reactions, which take a few days or months to complete. For example, rusting of iron. And the third is moderate reactions. These are reactions which have moderate speed and their rate is determined by common laboratory methods. For example, hydrolysis of esters, decomposition of H2O2, etc. Now we come to the rate of chemical reaction. Rate of chemical reaction is defined as the change in concentration of any of the reactants or products per unit time. Now suppose R reactant is converting into P product. So if 1 mole of R produces 1 mole of P, then rate of reaction will be decrease in concentration of R upon time taken or increase in concentration of P upon time taken. Now if R1 and P1 are the initial concentration at time T1 and R2 and P2 are the final concentration at time T2, then delta T will be T2 minus T1, delta R will be R2 minus R1 and delta P will be P2 minus P1, and the rate of reaction can be written like this. Rate of reaction is equal to minus delta R upon delta T or plus delta P upon delta T. Now these square brackets which are present around the substances, they are the molar concentrations. Negative sign in the concentration of reactants, it indicates that there is a decrease in concentration of reactants with time. And this rate of reaction, it is also called as average rate of reaction. Now let us take an example. Suppose we take the reaction PCl5 is getting converted into PCl3 and Cl2. So in this case, rate of reaction will be minus delta concentration of PCl5 upon delta T, because this is the reactant, so minus. Or it can be increase in concentration of PCl3 or increase in concentration of Cl2. So it can be plus delta concentration of PCl3 upon delta T or plus delta Cl2 upon delta T. Sorry. Now next is average rate and instantaneous rate. When rate of reaction is calculated or determined for a certain interval of time from T1 to T2, then it is called as average rate. Okay. So what we have studied till now, that was the average rate of reaction and it is represented by RAV. It is equal to minus delta R upon delta T or plus delta P upon delta T. But in case of instantaneous rate of reaction, instantaneous means at that particular moment of time. So instantaneous rate of reaction can be represented by minus dr upon dt or dp upon dt in place of delta R upon delta T and delta P upon delta T. See here it was minus delta R upon delta T. When you limit the value of T to 0, it becomes equal to minus dr upon dt. Similarly, delta P upon delta T, when you limit the value of T to 0, it becomes equal to dP upon dt. So instantaneous rate of reaction, R instantaneous, is equal to minus dr upon dt or plus dP upon dt. Okay, now graphically rate of reaction can be represented like this. If you plot concentration of reactants against time, you get a curve like this. But if you plot the concentration of product against time, then you get a curve like this, in the opposite direction. Okay, because reactants are decreasing and products are increasing. Now R average rate of reaction, it can be calculated like this from the formula minus delta R upon delta T, which is equal to minus R2 minus R1 upon T2 minus T1. And instantaneous can be calculated. T instantaneous is equal to minus dr upon dt, which is equal to minus slope. Similarly, here if you are calculating from products, R instantaneous will become dp upon dt, which is equal to the slope, or R average will become equal to delta p upon delta t, which is equal to p2 minus p1 upon t2 minus t1. Next we come to dependence of relative rates of reaction on coefficient of in the reaction. So for reactions in which stoichiometric coefficient of reactants and products are same, as in decomposition of thionyl chloride is SO2Cl2, rate of disappearance of any of the reactants is same as the rate of appearance of product. See, SO2Cl2 gives SO2 plus Cl2. So here also 1, 1 and 1. So stoichiometric coefficients are same. So rate of reaction will be delta SO2Cl2 upon delta T, that is minus because it is reactant, or delta SO2 upon delta T, this will be plus because it is product, or delta Cl2 upon delta T, again plus because it is product. But in certain chemical reactions, stoichiometric coefficient of reactants and products are not the same. For example, if you take this reaction, 2N2O5 is giving you 4NO2 plus O2. Here it is 2, this is 4 and this is 1. So for expressing such reactions, rate of appearance of any reactant or rate of formation of any product is divided by their stoichiometric coefficient. See here. For that reaction, now rate of reaction will be, because it was 2N2O5, so you will have to divide delta N2O5 upon delta T by 2. Okay, so it will become minus delta N2O5 upon 2 delta T. It was 4NO2, so it becomes delta NO2 upon 4 delta T. It was 1 O2, so this becomes delta O2 upon delta T. Alright, so the with the stoichiometric coefficient you will have to divide it if they are different. Now next we come to factors influencing the rates of chemical reaction. First is the nature of reactants. Chemical reaction involving rearrangement of atoms between reacting molecules to form products, if such type of reactant is there. But different reactants require different energies to undergo collision to form products. Hence rate of reaction is different in different types of reactants. So if the reactants are different, rate of reaction will also be different. Why? Because different energies are required by the different reactants to collide and to form products. Next is concentration of the reactant. Concentration of reactant is directly proportional to the rate of reaction. Third is temperature. Rate of reaction in most cases is a homogeneous reaction mixture. In a homogeneous reaction mixture is doubled or even tripled by increase of 10 degree Celsius. It means that rate of reaction is temperature dependent. Like if you increase the temperature from 5 degree to 15 degree, the rate of reaction can become 2 times or 3 times the initial rate of reaction. So it increases with increase in temperature for most of the reactions. Next is surface area of reactants. Finely divided reactants, they have large surface area, so they react more rapidly than bigger reactants. So the smaller the size of the reactant, the faster will be the rate of reaction. Next is catalysts. Many reactions are accelerated in the presence of small amount of substances which are called catalysts, and their action is specific for a particular reaction. Next factor is radiation. Now, photochemical radiations are affected in the presence of ultraviolet light. For example, H2 plus Cl2 gives you 2HCl. So this reaction, if it is taking place in presence of ultraviolet light, it will be faster. Next we come to the dependence of reaction on reaction rate on concentration. This is called as law of mass action. Now, law of mass action states that at a given temperature, the rate of a chemical reaction is directly proportional to the product of molar concentration of reactants, with each term raised to the power equal to its stoichiometric coefficient as represented by the balanced chemical equation. Now, what is the meaning of this? Here they are trying to say that molar concentration of reactant, which is also called as the active mass, it has to be raised to the power equal to the stoichiometric coefficient of the balanced equation. For example, suppose there is an equation like this: A plus B plus gives you C plus dt. So rate of reaction will be directly proportional to concentration of A to the power A, B to the power B, which will, or it can be equal to, instead of the proportionality sign, you can put a K over here. So constant, proportionality constant, K, A to the power A, B to the power B. Alright. So according to law of mass action, the rate of reaction is depending upon the molar concentration of reactants. Okay. Now this is a theoretical fact, and for this you need to have a balance equation to get the stoichiometric coefficient. Next is rate law expression. Now rate law expression, it tells about the actual dependence on rate of reaction on concentration of various reacting species. Now this is law of mass action was theoretical, but rate law is experimental fact and is always written for the slowest step or the rate determining step in mechanism of reaction. Now if a reaction is taking place in 2 or 3 steps, then the slowest step is called as the rate determining step. Why? Because that slowest step will take up the maximum time. So that will decide whether the reaction will be fast or slow. Now let us take one example. Suppose N2O5 gives 4NO2 plus O2. Okay. Now rate expression according to law of mass action, R will be equal to what? R is equal to concentration of N2O5 to the power 2. This is what should be the rate of reaction according to law of mass action. Now if you look at the mechanism of reaction, N2O5 first splits into NO2 plus NO3, then N2O5 plus NO3 gives you 3NO2 plus O2. Now in this, the first reaction is a slow reaction and the second one is the fast reaction. Now the rate determining step we say is the first. So rate of reaction in this case becomes R is equal to K N2O5 and stoichiometric coefficient here is 1. Okay. So the above this expression is the rate law expression or rate equation. Let us take another example. Suppose for this reaction 2NO2 plus F2 gives 2NO2F. Now rate expression according to law of mass action was R is equal to K NO2 to the power 2 and F2 to the power 1, right? But if you look at the mechanism of the reaction, this reaction takes place in 2 steps. NO2 plus F2 gives you NO2F plus F. This is a slow reaction. And then NO2 plus F gives you NO2F. This is the fast reaction. So again, rate determining is the slow reaction. So R will become equal to K NO2 to the power 1 into F2 to the power 1. Alright, instead of this was the theoretical, that is according to law of mass action, and this is the experimental, that is according to rate law. Is it clear? Now next we come to, so there is a difference between rate law and law of mass action. Law of mass action is theoretical, it should be this way, but experimentally it has been proved that this is how it is happening. So this is the actual. Okay, next we come to order of reaction. Now order of reaction is the sum of powers to which concentration terms are raised in rate law equation. Now order of reaction cannot exceed 3. It can be negative, fractional or 0. Like if you take an example, suppose there is a reaction A plus B plus C is giving you products. Then the rate law is given by rate is equal to dx upon dt, which is equal to K A to the power P, B to the power Q and C to the power R. So, you know, P, Q and R, why we have not taken A, B, C, because if you take A, B, C over here, small a, small b, small c, then that becomes law of mass action. But according to rate law, it is not necessary that P will be equal to A or Q will be equal to B or C, R will be equal to C. So, we have taken P, Q and R. So, order of reaction becomes N is equal to P plus Q plus R. So, and if you look at the order of reaction with respect to individual reactant, so if you have to find order of reaction with respect to A, it will be P. If you find order of reaction with respect to B, it will be Q, and order of reaction with respect to C, it will be R. Okay, now let us take a few examples of order of reaction. First, let us go to zero order reaction. Now suppose there is a reaction like this. 2NH3 in presence of platinum at 1130 Kelvin is giving you N2 plus 3H2. Now in this case, rate of reaction is equal to K NH3 to the power 0 according to rate law. So here the order of reaction is what? Instead of P you have 0. So order of reaction is 0. It is called as zero order reaction. Similarly, for first order reaction, suppose this is the equation. NH4NO3 gives you N2 plus 2H2O. Now rate has been found to be equal to K NH4NO2 1. So here the order of reaction is 1. Second order, 2NO2 gives 2NO plus O2. R is equal to K NO2 to the power 2. So order of reaction is 2. Now we come to unit of rate reaction rate constant. Now you know that rate is given if you look at the nth order. Suppose order of reaction we take as n. So rate will be given as rate is equal to K A to concentration of A to the power n. So concentration can be written as rate can be written as what? Mole per liter upon time. Concentration is K is a constant, it has no units. Concentration is mole per liter. Alright. Or K is equal to mole per liter into the power 1 minus n and time to the power minus 1. Now if you look at a zero order reaction. For a zero order reaction, value the unit of K will be what? Here it will become 1 minus N is what? N is 0, so it becomes mole per liter per time. Alright, for first order reaction, 1 minus 1, this becomes 0. Anything to the power 0 is 1. So for first order reaction, the unit of rate of reaction is just time to the power minus 1. For second order reaction, it will become 1 minus 2, that is minus 1. So the K will be equal to liter per mole per time. And for gaseous phase reaction, mole per liter is replaced by atmosphere or bar. So there, wherever you have written mole per liter, you will have to write atmosphere or bar if the reaction is gaseous phase reaction. So this is all for today. The remaining we will take up in our next video.